Okay. Hello, everyone. Hope you are doing very well. So the session I'm recording today it is for C570 Advanced Mechanics, and it is for lecture 15. Lecture 15. Okay. So I'm recording this for you, so you can watch it later on. Okay. So at this topic or at this session, we are looking at torsion of sections restrained against warping. So warping, as we discussed before, it would be the effect that can be happening on the cross section of the member as a result of torsion. Okay, so we want to discuss it better and understand it when we can have it actually. Okay. Okay. So what are the objectives? Objectives are we want to be able to identify the impact of restrained warping on the response of open wall sections. Okay, we want to understand the impact of restrained warping. Okay. So what are the issues we are having with warping? Okay, so let's say the question is what happens when the plane cross section is not allowed to warp. So as we discussed, when you're twisting, remember, you're causing deformation of the end of the member, as we discussed in like a non-symmetrical members, like rectangular sections, that can be happening. So your section would be deformed. The section as a result of torsion would be deformed. So what if we are constraining this motion, this warping action? As you remember from your statics in undergraduate, whatever you constrain, you're going to cause the development of force and stress. Okay, so if you constrain warping, you are you will be developing some forces and some stresses as a result, right? I would say some stresses and some forces as a result. So, what will happen if we are not allowed to warp? We will be having an additional restraint that reduces rotation. Okay, so in general, rotation would be less because again, some portion of the force you're applying would be used to warp, right? So some warping is gonna take some of the twist. So your rotation wouldn't be developed completely. The cross section wants to warp but cannot. Okay, the cross section wants to warp but cannot. So it means what? It means if you're constraining the warping in one plane, your system cannot warp. So you're going to develop some stress as a result of restraining or constraining your system. Okay. So here, this induces axial stress, normal stress. We're going to talk about it, what is the reason for that. But as a result of the constraint against rotation, against twisting, against warping, you will be having some normal stresses applied at the locations that we're going to discuss it here. Okay. Okay. So look at the system. This system is fixed at one end. Here is fixed. This end is free end. Okay. So if you have this system, let's see what's going to happen. So we are having a torque apply here at the end. Okay. So, okay. So before going to this writings, let me tell you here that so this portion on this plane, since it is fixed, right? So it is restrained. Restraint against warping. Against warping. Okay. So that is what I was talking about. In that section, in the fixed end, your system cannot rotate, right? So it cannot warp as well. It cannot warp. It doesn't let you to deform. The cross section cannot deform. It has to be just stay as it was before. This sort of resistance against warping is gonna cause development some stresses for you. That is the normal stress we were talking about. So in the fixed end, you're having a specific type of stress, which is a warping, the normal stress as a result of warping. Okay. Again, think about it. This is the fixed end. This is the free end. I rotate my system, I twist my system from the free end. In this fixed end, my shape wants to be different, the cross section, but you are not allowing that. This resisting against this motion, this restraint against the warping, causes development of normal stress in your fixed end. Okay. So, but something happens here. So this warping, if you think about it, well, it is restrained here, but as you go to the free end at the other side, you are having different behavior. Here at the free end, you are not resisting against warping because it can just deflect. It will be warped, but you are not resisting, so you are not causing development of any stress against warping. So if you think about it, from right, which is the fixed, to the left, which is free, you are changing the behavior. The stress as a result of warping is going to be to some extent, and maybe after some lengths towards the free end, the stresses as a result of warping would be gone, right? Because if you fix, you are causing warping stress. If it is free as you go to the other end, to the free end, it is being faded away, okay? So I put it in this way for you. So what you are seeing here in this portion, it is the result of this discussion I made. To some extent, you are dealing with the effect of basically warping, resisting against warping. After that, you are not having that. To some extent, you are having lateral shear. We're going to talk about why you're going to have this lateral shear as a result of warping, right? When you pass and reach to the free end, right, to this side, you are having predominantly torsional shear. Now the torsion, the classic torsion would be more effective compared to the warping that you had to the right side, okay? So what I say here, as we discuss, for example, from here, to this length, okay? On this length, we are defining alpha, right? And this alpha on the length, so again, it's just like something like this, to this, up to this length. That's what I'm trying to say, okay? On this length, we would say, okay, your effect is, you need to consider the effect of warping stress, right? From the fixed, the distance from the fixed end. After this point, all the way to the free end, now you're dealing only with the torsional shear stress, okay? So here is this restrained against warping, and I would say as you reach to this side, to this end, it is not restrained against warping. Okay. 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 So here, so let me do a little bit better job. So let's just write this fixed on top maybe. So so what I do, I write here that this is the fixed Okay. So this at the bottom, the alpha is distance where lateral shear is dominant. Is dominant. That alpha distance. Okay. So let's continue. Okay. So as we discussed, in free end, you're having a specific behavior. After that, when you're approaching to the fixed end, you're having different behavior. On the fixed end, you're having more of like a stress because of the warping. At the free end, you're having a stress due to torsion, right? Due to the twisting, shear due to the torsion, okay? So if we want to basically write the state of torque in the free end, what we are looking at. So if you think about it, we are having, so this portion, first of all, it is dominated by torsional shear because of the torsion at the free end, at the left side. You're having basically a stress, okay? And what you will have the state of stress as a flow, just because of having a torsion. This would be basically a flow of shear stress. Okay, this would be a state of stress. So here we can define the torque. The torque, let's call it T2, represented the free end. The free end. Okay. T2 is equal to J G theta. Okay. So over here, for the free end, we define the torque as we have learned before. Okay, and we have seen this expression just for define the torsion. Okay. What if we go towards the support when we are within that alpha? If you remember, that alpha was the region that the warping was effective. Okay, next slide. Now we are near the support, dominated by the beam bending of the flanges. Okay, so in warping, what we would say, so that's our assumption. We say in warping, the two ends, like if this is the cross section of the member. So the top and bottom portion of the member, this would be basically, how can I say, govern the behavior of your cross section in terms of warping. When you are restrained in warping, the two ends, the top and bottom of your cross section would be effective. So the shear develop in top and bottom was gonna cause the warping behavior, or they're gonna govern the warping behavior and warping function, basically. Because if, however, these boundaries on top and bottom, they change, or they, in other words, they have the shear, depends on their shear forces develop, they're gonna say how this plane would be changed. They're gonna govern the whole cross section in terms of warping. Okay, so that's why we are so we're gonna talk about this step, one step at a time, right? So I'm gonna tell you why we are saying bending of flanges. First, I just start to tell you that, okay, we are having flanges on top and bottom to govern your behavior. Second thing, there will be shear developed. on top and bottom. They're going to cause you the deformation. And what is that shear? So we would say, for example, you're going to develop like this shear force. Let's call it V prime on top, and this shear force at the bottom. Okay? So these are your flange shear, flange shear. Okay? So again, you are going to have a torque here. Now let's call it T1, representing the fixed end where we have the restraint against warping. And this would be the dominant behavior. So if we have this case, let's find the relationship between the shear forces and the torque. Well, as you can imagine here, and don't forget, see, just a point here for us to just follow right away. The way that it is being drawn, we are assuming these shears are at the mid height of your flanges, flange thickness, okay? So if we find the relationship, you're gonna have T1 to be equal to V prime H, right? V prime H. This would be your expression. So first step, we found the torque behavior at the free end, which was second behavior, the previous slide here. This is the free end. At the fixed end, where the warping restraint would be causing development of some new type of forces, a new type of stresses, the torque is equal to V prime H. Again, why we are making this assumption? Because the boundaries of your cross section would govern what would be the response against warping and restraint against warping, basically. Okay, behavior of your cross section. Okay, so these are the two ends, 1 and 2, fixed. For the fixed, we said 1. For the free, we said 2. What about the intermediate locations? Something at the middle. So as you can imagine, something at the middle would be having both, a portion from both cases, a little bit from the fixed and a little bit from the free end, right? So if I want to quantify this, so think about it. You have, so both you're gonna have the both cases, right? You're having the shear. So this is like a red line. It is your basically coming from the free end, the torsional shear, right? Right, because as we understood, that would be basically the shear flow as a result of torsion. But these green ones here inside, these are the result of the warping. Okay, so now we have both of them at the same time because we are somewhere at the middle. So we have a little bit of that behavior, a little bit of this behavior. So what we assume, we are assuming at this section, you're having the rotation of beta. Okay, so like basically the angle of twist in this cross section, which is arbitrary cross section at the middle of your member, at the middle of the length, somewhere at the middle of the length is beta. So as we discuss here, in this case, you're having combination of lateral and torsional shear. Lateral and torsional shear. So I can call this one lateral for you to have a consistency in your writings. Warping shear force, can say lateral as well. Okay. So if you think about it, to torque in this case, so let me just draw like a torque here. Now this, I shouldn't write probably with the red. Let's just write it with black. So torque here would be a portion from lateral shear, which is warping really, and a portion from your torsional shear. jg theta. Okay, this would be your expression when you're at the intermediate cross section. Okay, so now you have two unknowns, this guy, this portion, and this portion. These two parameters are your unknowns. Unknowns that you want to find. If you find this, you can quantify the amount of torque applied in any intermediate section. Okay. Now, let's a little bit dig more into the problem, and so we can quantify the problem better. Okay. Okay. So let's look at the system. First of all, we are looking at the top view. This is the top view of the cross section. So this is the I section. So think about an I section, right? This is the cross section of I section. You are looking at from the top, right? And at the end, you are twisting the member. Okay. So if we have this system, so if you think about it, by applying torsion at the end, you can have some lateral deflection. Lateral, if you think about it, if you start to twist, especially these non-circular sections like this, what's going to happen? You're going to have some deformity that push your system a little bit laterally as well. Okay, so a simplification of drawing, I would say something like this maybe. If I can draw this, that'll be great. Okay. Sorry guys, let me just do a better job. Okay. So what we assume, we would say you are having some lateral deflection, we call it X. Okay, lateral deflection, we call it X. Okay, and don't forget about the other direction. The other direction is X, and Z is your length. Z is your length. Okay. So as we have discussed before, in so a little bit, I want to just like a little bit work with the concept of the using basically the angle in each section, right? Using an angle in this section. So just like look at this previous slide here. So if you think about it, I used to be here, now I moved here, right? So this beta would be telling me, okay, what would be the moving towards like x-axis. On the x-axis, like how I'm moving to the left, right? So if you want to understand the x, you want to use the beta because beta is going to tell you how much you're going to move. So if you think about it like mathematically, we can use trigonometry, right? So we can define this expression. We can say x is equal to h over 2, the half height, because you know that there is a rotation, right? So if you use the half height, it would be, this would be enough, times the angle of twist in the cross section, right? Just using the trigonometry. So if we have this basically relationship, let's make one derivative. If you make one derivative from both sides in respect to z, so you would have what? You would have dx over dz square, dz, right, is equal to h over 2 d beta over dz, right? This is one. Let's make another derivative. If you make another derivative, it would be dx squared over dz squared is equal to h over 2 d squared beta over d z squared. Okay, we will have this expression. Now, your and also from before, if you remember, from before we knew this expression, we knew that d beta in respect to dz is theta. The rate of twist, the rate of twist over the length. You remember that we have assumed the theta, and exactly we said this. We said the change of angle in respect to length. What we are talking in the realms of derivatives, right? So we can just express this expression. We can conclude this expression. So if that's the case, what you can say, if I put it in here, so d beta in respect to dz is theta. This is the second derivative, so it would be d theta over dz, right? So here we can say it is equal, so we can say, let's write it, dx squared over dz squared is equal to h over 2. Now this guy is the derivative of theta in respect to z, right? Derivative of theta in respect to z. Okay? As we discussed, this theta, I'm sorry, guys. I'm so sorry. Okay. As we discussed, this beta here, this theta is the unit rate of twist. Unit rate of twist. Okay. This is our expression. We have found this last expression. This is important, right? So far we have learned this. Okay. Now, also let's just recall something else. Something just from before, from your undergraduate. If you remember, so I would say let's recall EIY over 2 times second derivative of x in respect to dz squared is equal to negative my. Okay, this expression, it is for basically bending, the relationship between bending and elastic curve. If you remember, the elastic curve, which was a deflection of your member, was basically the second, the second derivative of the elastic curve, right, in respect to the height, was equal to m over ei, right? So I basically find this expression where I just move the ei to the other side, and I write this expression. The only thing I have added is over 2 here. Why? Because I'm writing for one flange on top. So this is for a flange. And why I'm writing this? Because this twisting behavior warping behavior, the way that it affects you, it is very similar as if there is a shear force applied laterally to your member. The behavior is like that. So that's why I sort of write this last portion to tell you, okay, now what I do, I assume in a way that there is a shear force applied from the side, from lateral point of view to my member, and causes like deflection. Look at this deflection. So we used to have like forces applied vertically to your beams, like back in undergraduate, so you can find the elastic curve. Now what I assume the lateral force applied to my member, right, causes the deflection laterally. Now write exactly the same equation. The only assumption I'm making here is that I'm dealing with Iy, because now this lateral motion is what I'm gonna scrutinize. So I need to use Iy, and also moment would be about y-axis. So basically I switch the vertical point of view to lateral point of view. Okay? Okay, so we got this portion so far. We have understood this relationship here, this guy here, and also we have learned this guy. So what I do, I'm gonna mix these two concepts in the next slide. So look at it. Okay, so let's write this. So E I y over 2 times h over 2 times derivative of theta in respect to z. So basically I just mixed these two concepts. I'm going to show you again. Is equal to negative my. So look at this. This portion, this guy here, right? I just put it here. That's it. That's it. I found this portion and put it in this equation. Would be this expression here. Okay. So also I want you to recall that V prime, the shear, is derivative of moment in respect to length, right? Remember this? Okay. So what I do, I make a derivative from both sides again. If you make a derivative from both sides, what you're gonna get? The constants would be there, no problem with them. This guy would become the second derivative, right? This guy also would be negative derivative of my in respect to z, which we have here, we have found it is equal to negative v prime. Negative v prime. Okay. Now, based on what we have seen, we are seeing here, we define a constant value. That is going to be familiar for you. Look at it. So we define alpha to be equal to h over 2 square root of e I y over jg. Okay, as a result of, so basically in this expression, it would be useful for us if we have this assumption so we can write the equation easier. So knowing everything so far, I'm going to rewrite that equation you saw in slide 7 here, this equation. Finding what you have found so far, I'm going to rewrite this expression. Okay, so let's look at it. I can write the equation one more time here. So t is equal to v prime h plus jg theta. This is the equation, right? So based on what you have learned, what you have found for v prime, I'm going to rewrite this expression. And if you rewrite it, you're going to get negative alpha squared d squared theta in respect to dz squared plus theta is equal to t over jg. Okay, this is the total, right? This is the total. Okay. So this would be your expression. We have found a good expression in terms of theta, only one unknown. V prime, we have found it already in terms of theta. Now the total equation of torque is expressed in terms of theta. Okay, again, just mathematics. If you just look at it, you would understand. If somebody's asking, okay, how did you get this from what I found V prime at the previous page? It would be very basic mathematics. So just can be found if you could just spend like 30 seconds probably looking at it. Okay. So this is what we have found. Let's just keep this one for now. Quickly, let me tell you something, and that is sometimes in AIC, which is a steel code, you would see alternate form of alpha. So alpha can be expressed with this expression, CW E over GJ, right? So this is AISC warping constant, which is CW. I'm going to write it for you. Constant for I section. Okay. So CW is this. So CW, if you ever want to find it, would be equal to IY H squared over 4. Okay, so basically what you're having exactly the same alpha, but you're just sort of how can I say, they sort of like factor out these parameters and say, okay, let's call this CW, and in the code for each I section, they're gonna give it to you, so you can just directly use it. Makes the life a little bit easier, but they are basically the same concept. The alpha is this here. You're gonna get the same answer, but you can read a little bit more information from the table, so it makes the life a little bit easier because you can read the CW from the table and then just plug into the rest of the alpha. Okay. Let's go to the next slide. Okay, so now what we do, we try to solve that expression. We are solving this guy, right? This guy. We are trying to solve this. Okay. If you solve that, this would be your answer. You're gonna find theta. You're gonna find theta. You're gonna find beta. So solving backward, that's like a differential equation. You find it, and then from that you can find the beta, right? Because you know the relationship between alpha and beta. This was this relationship, by the way, just to remind you, was right. Okay, so we can find the beta. So if you find these two, you can find the moment. Again, moment, we have said it here. Here, look at the slide. Where was it? Here. You can find the bending moment about y-axis as well, right? So you can find my as well. Okay. So these are your answers. There's no assumption, like your definite answer. And as you can see, hyperbolic tangent here, like hyperbolic cosines, tangent, sines, it is being used because of just mathematics. With the way that you find the answers, you're gonna have these expressions. So now, if you have lengths over alpha, what was the alpha? Alpha was the length from the fixed end where the warping is gonna cause lateral stress for you. You need to consider that, okay? If L over alpha, you find, is more than 2.5, so this tangent would be equal to 1. The tangent would be equal to 1. So your expressions would be a little bit different, would be easier, right? It's like simplification. So if it is L over alpha is more than 2.5, we can have some assumptions. Okay? We're gonna look at them further, but let's look at the section one more time. Okay, so this is your section here. Here is fixed, right? So this is the alpha. You're in the alpha region, right? Alpha region. So in alpha region, look at this. You're gonna cause development of some shear forces, as we discussed, some lateral shear forces. Okay, lateral shear forces. So this again, lateral shear forces you're causing is gonna cause development of the bending stress. Bending stress, right? So again, just very similar to what you had learned undergraduate. You had forces coming vertically, causes development of bending stress on the height of your member. Now you're having force laterally applied as a result of the warping. So you're having normal stress develop into the width of the member. Okay? So what we have here is bending stress. These are the bending stress on the width of the member now. Okay? Okay. So what will happen in your member? So if you draw the beta in terms of lengths, so at the beginning of your system, the beta would be affected by the warping behavior. So it is not linear. It is not linear. But as you pass from the alpha region, which the warping was effective in this region, your system is, the beta would be basically linear for the rest of the region because only the twisting is working for you. Only the twisting shear is working for you. It would be like a classic torsion, in other words. So this region, let's call it rotation. Rotation of torsion, it is linear. Okay, but we couldn't say that within the alpha interval. Okay, so one side from alpha towards the free end, you're having torsion, right? From alpha to the fixed end, you're having warping. Okay, so now let's separate these two. If we are just talking about only one of them, what would happen? What would be your equations? So I give you the expression here. T2 is the pure torsion portion. Pure torsion portion. Meaning that if you remember, what was the equation we have started? Look at this equation we have started from the beginning. Here. We have started with this expression, right? This guy was for pure torsion. Right? This is T2 that you're going to see it later. T2 that you said later would be this expression because this is for only the torsion out of basically the portion that the behavior is similar to out of alpha portion. Okay. Okay. So this would be the pure torsion portion. So if you draw this, look at the next page. If you draw this T2 over T, right? Because you have the T2 here and you have the T here, right? So this graph is what? Portion of the pure, meaning what? Meaning it is T2 over T on y-axis and ratio of the lengths, which means basically it depends on like how much of the lengths, like Z over L, basically. Z over L. If you draw this for alpha equal to 1, for alpha equal to 1, okay? if you draw alpha, if you make the alpha equal to 1 in this equation and draw it, you're going to see this behavior. As you can see, T2 have been started to go to some extent, and then almost from some point forward, like maybe after like this point or this point, here you're more of dealing with the pure torsion only. Pure torsion only, because, well, you're just getting to the free end, so only the portion of the pure torsion is working. You're just getting like 100% of the torque, really. Okay. So now what we do, let's assume that the L over alpha is more than 2.5. Let's look at it here. Okay. So these expressions you are seeing here, so if you look at the beta here quickly. Let's look at a slide number. Yes, slide number 11. So this was your beta, right? So I'm assuming this is going on. If this is going on, it means what? This portion would be equal to 1, right? So what I do, I rewrite the expression in this term. So this would be this expression, right? The beta would become this. So here I just want to write that if L over alpha more than 2.5. Okay. This would be the value for beta. This would be value of my max, T alpha over H. Your sigma maximum bending stress would be what? Well, you know that is my over I, right? So you will be dealing with m y max multiply by, so now you need to use basically, you are on the flange of the member, right? You're on the flange of the member. So for writing the bending stress on that, you want to say the mid widths, because the widths would be the total basically widths. So mid widths would be what? Would be over 2, right? Be over 2 over I, but don't forget you are writing the equation in terms of only one flange. So let's write it I y over 2 for a single flange. Okay. So if you write the answer to this expression, you're going to get 6t alpha over ht b squared. This would be your maximum normal stress. Okay. And also here, I want to tell you that your Iy over 2, so for one flange you want to write, right? So for one flange, you have to write this as b third t over 12. Okay? Over 12. Why? Because it is for a single flange. Whereas we have two flanges that being involved in these problems and the strength of your member, really. Okay, these are the equations we have learned, right? So one end was fixed and we have derived all these equations. So if warping is restrained of both ends with C table. Okay? I want to say restraint at both ends, I would say. Okay. So in this case, we want to look at some table that's going to helping us to find the formulations we need better. So let's look at the formulations here. Let's look at the tables. Okay. So in this table, you're having both ends are fixed. Both ends are fixed. You are having torque applied, like one external torque applied to the ends, right? If you have this case, we give you maximum moment, right? Maximum moment. And if L over 2 alpha is more than 2.5, which is what we have discussed before, you're going to use this formula for the maximum moment. Again, maximum moment. Why we are having moment? Because we are talking about lateral. We're talking about the warping. It is giving you the warping moment, bending moment in the lateral direction. Let's look at the bottom one. In this case, you are having distributed load. Distributed load applied on top of the flange, and both ends are fixed. Both ends are fixed, right? So if you have this W as a distributed load applied to your system, okay? So well, the torque would be equal to this WL times E, and would be the eccentricity basically. And E is given to you here. Okay? Your maximum moment can be found from this expression. And again, if the L over 2 alpha is large or more than 2.5 as a rule of thumb, we told you, you're going to use this expression for maximum moment in this case. Okay? Let's look at this one. One end is fixed. You're having W applied. Torque would be equal to this expression. Maximum moment can be found from this expression. Again, if L over alpha is large, you can use this formula. Okay? At this one, you're having only 3 spots to be fixed. This spot is fixed, this spot is fixed, this is fixed. So this is very, we can model this with the softwares, with like a, safe, not the safe, with the SAP, sorry, with the SAP, we can model this and just put those 3 spots to be fixed, right? And the shape of the torsion is now with these 2 guys applied to your system, okay? If we have this case, maximum moment can be found with this expression. If we have this rules going on, you can use only this guy, okay? These are like a couple of scenarios that you can possibly have. So we just introduced them to you. Now, let's look at an example here. So this example is 6.60 from your text anyway. So let's make sure that you're having understanding of it. So in this problem, you're having a force applied with eccentricity, and the length of member is 1600 millimeters. This arm is 100 millimeter, right? We are asked to find the P such that the maximum normal stress is 160 megapascal in Z direction. In Z direction. For direction, don't forget, this is X, this is Y, and this is Z. Z is the length. Maximum normal stress to be as the direction to be 160. Okay, so this problem, you can have a bending stress, you can have warping, you can have torsion. So let's look at this problem, how we can deal with this problem. So the first thing we are doing, we are finding the moment of inertia of the flange, because that's what we're going to use a lot, right? Moment of inertia of the flange would be, well, using, like, look at this. This is the flange. You're having 6 and 60 millimeters for flange, right? So what we do, we would say moment of the inertia of the flange is BH third over 12. Let's multiply it by 2, right? Let's multiply by 2 because we have 2 flanges. So you would find 2.16 10 to the power of -7 meter force. Okay. Then let's find the torsional constant. Torsional constant, as we have learned, it is one third of basically the height times width to the power of 3. Okay. So how we can find it? So you have like a 2 flanges. So width times thickness, because the smaller one goes to the power of 3, right? Plus, then we look at the your web. Your web is what? Your web is 6 millimeter in thickness and 80 in height, right? So a smaller one goes to the power of 3. So here you want to pay attention to one thing here. And for the height of this member, don't forget what we assume we assume this shape. Right? This height is 68 millimeters. That's why we use 68. Because like 6 from top, 6 from bottom, minus 80 would be 68. That's what you see here. Okay? 1/3 of this, guys, is going to give you the torsional constant, right? The answer to this would be 1.35 10 to the power of -8 meter force. Okay? Now let's find the alpha. Alpha is a constant, so the h of your member. Okay, this h, what was that? Was a tricky point for you. Don't forget the h here. H is going from the mid height. Remember this discussion? This h you're using going from the mid height, because this h is the distance between the lateral shear forces. If you remember, I said we're gonna assume that the mid height of your member. So this h would be what? Would be 80 minus 1 thickness, basically, because half a thickness from top, half a thickness from bottom. So it would be 1 thickness. So 80 minus 6 would be 74. Okay. So let's enter it here. So your h would be 0.074 over 2 multiplied by moment of inertia. Sorry, the modulus of elasticity is 72 10 to the power of 9. Your IY, we have found it here, 2.16 10 to the power of -7. Okay. Over G. G is given to you actually in this problem as well, 27.1 10 to the power of 9. And J. J, we have found it here, 1.35 10 to the power of -8. Okay. This would be equal to 0.241 meters. This would be your alpha we were discussing. The alpha would be where the lengths that the warping action is significant, right? Remember this? Okay. So you have found this. Now let's find alpha over L over 2 alpha, because you need it, right? You want to find this because this is going to tell you what equation would be simplified for you. So you're not going to just go with that hyperbolic tangent and cotangent and sine and cosine. So if you do that, you have 1600 millimeters, which would be 1.6 meters, right? right? If you find this, your answer would be 3.32. Okay, it is more than 2.5. So what you're gonna do, you can assume, I write it here. You can say your maximum moment is equal to T alpha over H. So I do in this way, so you know that that would be the rest of the problem, this side. Okay, that's our assumption. When the L over alpha is more than 2.5, or L over 2 alpha is more than 2.5, you can use this expression. Okay. It is it is very similar to the case 1. So that's why I say L over 2 alpha. Case 1 that we describe here, like this case 1. It is, we can say it is similar to this. So that's why we are assuming that. But yeah, in general, L over alpha, L over 2 alpha is large, so we can go with the simplification, okay? Both numbers would be good estimation. They wouldn't be that far away, really. Okay. Let's go for here. Okay, we have found this. Now, let's write our equation. So first, internal forces at fixed end. What internal forces do we have? Well, torque would be what? Look at the torque. Torque would be force times this arm, right? This would be the torque. It's going to twist the member about this axial member. So axial or longitudinal axis would be force times 0.1 meters, right? My max, it is equal. So my x, we have found it is equal to, we can say it is equal to T alpha over H, right? So what do you have? You have P times 0.1, right? This is what we have found for the T. Alpha, we have found 0.241 over H is 7.74. Okay, so this guy would be 0.326 P. Okay, this would be my max in terms of P. Also mx, you're pushing the system down. You're gonna have mx as well. That's what you have learned before. So mx in this case would be, well, look at the system. Look at the system here. Again, now it would be this force multiply this length. Moment about x-axis, right? Twist the member about x-axis. So would be equal to what? P times 1.6 meter. Okay. So now let's find the normal stress. Normal stress due to the torsion. You know that warping is going to give you the normal stress. We have discussed this before. So let's find the stress corresponding to this. Stress corresponding to this. So what's going to be the stress corresponding to this? It's going to be my max basically times z over 2 times I y over 2. We have shown this expression in the previous, like 2 slides before. So my max, we have found 0.326 P times B over 2. Well, the width would be 6 millimeters, 0.06 millimeter, sorry, 0.06 meters. So over 2 would be 0.03. Okay. Over I, over 2. So what was the I we have found? The I that we have found is 2.16, but let's divide it over 2 because I over 2 would be in the expression. I over 2. So would be 2.16 10 to the power of negative 7 meter force over 2. Okay. Your answer would be 9.06 10 to the power of 4 P. Okay, this would be your normal stress as a result of warping. Okay, this is one normal stress in your section. The other normal stress would be as a result of bending, just regular bending you have learned in your undergraduate. So let's look at it. This is normal, like by normal I mean classic, the one that you have learned before. My over I, but this is about x-axis. The traditional one is about x-axis, right? Mx times the height over 2. Height over 2 would be the maximum distance from neutral axis, right? Over moment of inertia about x-axis. So again, you know this, we can just write, I don't know, like this M is, we found like 1.6 P, right? 1.6 P. And the I is the problem given us like 1.145 10 to the power of negative 6. Okay. So if we have this, the answer would be 5.59 10 to the power of 4 P. Okay, so you have found 2 normal stresses, right? One of them about y-axis. So let me show it this way. One of them about y-axis, one of them about x-axis, right? So like I show you like this. So one of them is like this, one of them is like this. Okay. So this is like, if you remember in undergraduate, again, we had the combination like a biaxial bending. Remember biaxial bending? So you know that these two guys, there would be one of the quarters that both of these two guys would be positive, or both of them would be negative. At that portion, it's going to hurt you. It would be the maximum. You need to add them. So let's consider that worst case scenario by saying that let's look at the total normal stress to be the normal stress due to the torsion plus normal stress due to bending. Okay. So you will have 9.06 10 to the power of 4 P plus 5.59 10 to the power of 4 P. These are equal to your total allowed. The problem says 160 megapascal, right? So 160 10 to the power of 9. Okay. One 60. Well, I don't think it is to the power of 9. Should be 6, right? It is to the power of 6. So So it would be 1092. 10.92, 10 to the power of 2. 1092 Newton. That is the answer. I have 10 to the 9 here, but I don't think that's correct. I think this is correct. Okay, this is the allowed P that can satisfy your problem, and you're not gonna pass your allowed normal stress for this section. Okay, so just continue. So we have one concept, torsional stiffness, very similar to the stiffness we have defined before in our different topics. It is very similar. So the stiffness is the torque required to produce a unit rotation, right? We have this expression of beta in terms of T, we have learned it before. So the only thing you're gonna make this guy equal to 1. If you find the theta in terms of beta is equal to 1, it's gonna be, we call it the stiffness. Okay, if you find the T, that's for everywhere. If you put the deflection equal to 1 and find the force corresponding to that, it's going that force you find is going to be the stiffness for your system. Same thing for the torsional. So torsional stiffness, if you do that, T if equal to this expression and you put everything at the other side when the beta is equal to 1, this would be your torsional stiffness. Okay. And also, again, recall that alpha is equal to this expression because you need it. Okay, this is one thing. Okay, this is your, again, torsional stiffness. Second thing, let's look at this graph here. So this is like an I section in your basically code, in the AIC code. Okay, so for example, for this section, you are seeing that you are given different information here. I don't know, like this depth of the member is 12.2. This thickness of the flange is 0.64. Moment of inertia about y-axis 107, right? And this torsional constant CW giving you to be 3570. But we have learned CW already, right? Previous slide I showed you as well. Here, CW. That's something you need. So AIC, the steel code gives you sort of like an insight, really, basically. So if you think about it, what you can say here is that, so what is your H? Your H would be equal to, well, the D is the total depth, right? 12.2 inches minus, so the thickness of one of the flanges would be the H, because H, again, it goes from, look at the H. H is going from the mid height to mid height. Okay? Minus 0.64 is going to give you 11.56 inches. Okay? CW, if you want to find it yourself, we have given you this expression that you can say H over 2 to the power of 2 IY, right? If you just plug in the numbers, H is 11.56 over 2 to the power of 2. I, again, we read it from the table, 107 into the power of 4. If you find it, it would be equal to 3775 inch to the power of 6. Okay? Again, look at this. This guy was 3570. This guy was 3575. The reason, because of a little bit they are different, because you're having some fillet in the I section. In the I section, some fillets here, like this fillets are a little bit changing changing your behavior the way that they come. So they are not quite like a rectangle to rectangle. They are having some sort of transition using a circle, right? This would be one thing for you. And the last thing to discuss, sorry guys, we are getting like a few minutes over our time. Let's just finish it because we have basically nothing left. So here, very quick, you're having a section here, an I section. So for this section, so the shear center and the centroid, they are both at the same point, okay? Moment of inertia, sorry, the torsional constant can be found with this expression, which is basically you use the width and the thickness of flange, two flanges and one web, right? Two flanges and one web, right? CW given you can use this expression for this, like if there's a symmetric I section going on with you. Polar moment of inertia would be the summation of Ix and Iy. So polar moment of inertia and torsional constants are different. We're not going to mix it at all from now on. This unsymmetric or non-symmetric I section, again, moment of inertia. Now, instead of having like two flanges, like which is the same, you're having two different flanges. So you're just going to use its coordinates. 1/3 of that. CW, you can find it with this expression. Moment of inertia, again, would be Ix plus Iy. Now, here, I just want to tell you, we're going to go back to this point and we're going to talk about this shear center. This shear center will be discussed later on with us, right? But here, I just want to quickly tell you that this distance y0, which is from the torsional center, sorry, the shear center and the centroid of the cross section, this distance would be used when you're trying to find the polar moment of inertia. And also to answer you the height of the shear center, it can be found using E. Shear center would be a point that if we apply the load on that point, the system won't rotate, won't twist. We're gonna learn it more. We're gonna learn it more in this course. We're gonna discuss how to find it and what exactly it means. But here, just because it is related to twisting concept, I just told you at this spot as well. And here is like a couple of more sort of consideration for you. Again, torsional constant, CW for this case. As you can see now, again, your shear center would be at this point, right? Here, if you have like a channel, an angle, you can deal with this J's and this CW's. Again, for the channels, it is the most famous for this shear center would be for the channels. Look at where the shear center will be located. It is like basically away. It is outside on the other side. Okay, so that's it. Having this said, please make sure that you watch this video. And the next, I'm starting next Tuesday. I will be starting after the session, which is I'll be starting from lecture 16, basically. And it would be good for your homework right now, the next homework number 6. Thank you guys, take care, and see you next time.